So I promised to Anik to speak in English. Apologize for this. And yes.
Нет, с микрофоном все хорошо. Странно. Ну, кроме как нажать на эту кнопку, в целом нет другой опции. Но ничего не идет.
Не идет трансляция?
Да.
А запись?
Запись можно, но я не знаю, куда она сохранится.
Нет, просто если она не идет, то можно по-русски говорить. Я вот к чему.
Ага. Ну, вообще говоря, чего-то не идет.
Ну, слава богу.
Ну, видимо, ладно.
По-русски, но слава богу.
Но я сейчас напишу, возможно, ее не туда записывают. Такое бывает. Какая-то из лекций записалась как лекция по геометрии для первого курса.
И как первокурсники?
Ну... у них...
Это Шварцмана или Городенцева? Граденцева?
Граденцева... Не, у них Граденцев алгебру ведет, ну как у нас. А геометрию Амбург.
Амбург.
Да, там. Странно, конечно. Ну ладно, но, видимо... Но я напишу, возможно, она записалась, но, видимо, записи нет.
Ну, слава богу. Хорошо, значит, сегодня вот мы будем решать уравнение методом Ньютона, но сначала, совершенно безотносительно к этому, я должен рассказать лемму Дворка, потому что вообще она полезная и употребляется в упражнениях. Собственно, она еще употребляется в доказательстве Дворка рациональности зета-функции, но что-то я боюсь, что, может, мы до этого до конца не дойдем. Значит, рассматривается ряд f от x, сумма аита x в степени ита, значит, у него p-адические коэффициенты. Вот. И нас интересует вопрос, вдруг они целые. Значит, утверждается, что коэффициенты действительно целые, тогда и только тогда, когда дробь f от x в степени p делить на f от x в степени p тоже имеет целые коэффициенты, даже делящиеся на p. Вот, скажем, это будет называться g от x. Доказательство в одну сторону совсем просто. Если f от x действительно имеет целые коэффициенты, то f от x в степени p равно f от x в p-той. Здравствуйте.
Вы сказали, что у вас тут проблема с трансляцией. Нажал на нижнюю, где трансляция на левую кнопочку.
На левую? Да не может быть.
Не, я просто спрашиваю, на левую нажал? Сам разберусь, что боюсь.
Окей. Но вы предупредите, когда запись начнется, да? Хорошо. Значит, можно написать так, плюс что-то, что делится на p. Ну и тогда частная будет 1 минус p g от x делить на f от x в степени p, но и будет иметь коэффициенты 1 плюс все остальные, которые делятся на p. Это хорошо. А обратно нужно будет по индукции доказывать. Ну, а просто f же начинает с единицы, поэтому когда мы делим, ну просто по формуле там геометрической прогрессии. Вот. Значит, обратно, значит, напишем f от x в степени p равно f от x в p умножить на g от x, и напишем g от x сумма b итых x в степени i. Вот, а f это сумма a итая x в степени i. И будем доказывать по индукции. Значит, что? Пусть мы знаем, что коэффициенты целые для i меньше n, хотим разобраться с n. Значит, посчитаем коэффициент при x в n в произведении сумма аита x вытой на сумма b житая x житой. Ну, поскольку мы знаем, что получается f, сейчас только это в p-той степени, прошу прощения, поскольку мы знаем, что получается f от x в степени p, то у него коэффициенты, которые не делятся на p, вообще нулевые, а которые делятся на p, они соответствующие n-ные. Значит, он равен a n делить на p, если n делится на p и 0 иначе. Просто по предположению нашему. Вот. Да.
Короче, трансляция идет, но она просто идет в доступ по ссылке.
Она, в общем, не туда опять идет.
Она, да, не туда опять идет, потому что Гоша, видимо, не настроил ключи классов,
Так.
чтобы она в 427 ушла.
Ага.
Поэтому сейчас вы, скорее всего, где-то в Амбурге транслируетесь и в закрытом доступе, потом выложим.
Да, потом...
То есть все-таки нужно по-английски говорить, да?
Ну, видимо, к сожалению.
Ну окей, спасибо, хорошо.
Можно по-русски, просто будет запись потом на русском.
Да, я понимаю. Спасибо. Okay, so I have to continue in English. Pardon me? This? Just because we have this equality by assumption. So we're okay. On the other hand, let's just write down explicit formula for this coefficient. Well, so calculate the nth coefficient of this product. And subtract this coefficient a n over p x to the n if p divides n. So we know that the coefficient a n over p is equal to n a n over p to the power p modulo p. But just any number has any integral number has such a property. So we get the 0 coefficient over x to the n, because we subtracted this, yeah, equal to the sum of terms, one of which is just p times an, and all the rest lie in p zp by the induction assumption, because we already know that all the smaller coefficients are divisible by p. And hence we know that p an lies in p zp, and hence an is integral. Okay, so this was an aside. It is not needed for today's lecture, but it's only used in the exercises, and maybe will be used towards the end of the course. But what we actually wanted to do today was to solve polynomial equations over power series or Tate field. And to this end, last time I introduced, in addition to Newton polygons, I introduced the Newton broken lines. So how does it work? Last time I gave a definition. Let me repeat it. So gamma of a polynomial phi. Phi is the sum of ai x to the I. We will only need it for polynomials, not for series this time. And this is the graph of a function gamma of alpha, and this is the minimum of certain linear functions. So the whole thing will be piecewise linear function. And linear function Li is I times alpha plus the p order of the of ai, the coefficient here. Okay, so we had an example last time. Losha drew an example, but he's not here today, so I'll reproduce his example. Phi of x is 1 plus x squared plus 1/3 x cubed plus 3 x to the fourth, and p is 3. Okay, so I will need -1, -2, -1 here, -2 here, -3, -4, -5, -6, and -7. Well, maybe it's not very good, but still. So I have -1 here, -2 here, maybe also -1 here, 1 here, and 1/3 here. And well, I have this line. Okay, and this line. But also we'll have one more line which passes through point 1 here. Somewhere there was different color chalk. So to this line. It goes to here, and then it goes to all the way down, but I have no space for it. So this Newton broken line consists of 3 pieces. This horizontal piece going from 1/3 to the right, then this white piece of certain slope, and then this green piece, which is also infinite and it has even a bigger slope, but unfortunately it doesn't fit into this blackboard. Okay, this was the result of Losha calculation last time. And maybe to compare, let me draw the Newton polygon. It starts from the origin. And while it goes to -1 here, and then to +1 here, and that's the end. So it's gamma, and that's n. So this is convex, I don't know how to say, from below. And this is convex from above. Okay. So in general, there is a bijection. Between the vertices, or maybe say the edges of the Newton polygon and the vertices of the Newton broken line. like here, we had two vertices of gamma and two edges of n, right? Such that the x coordinate, well, maybe it's an unfortunate name because this x is our variable. There's a Russian word abscissa. Probably it also exists in English. I'm not quite sure. And if it exists, how is it spelled? Without Masha Verbitskaya, I am at a loss. So something like this. So the x coordinate of the vertex sorry, is the negative slope of the edge, the corresponding edge, and the length of the edge is the negative difference of slopes of edges of gamma containing this vertex. So maybe I should draw another example to illustrate this principle. Like, well, you can also see it here, but maybe to better fit into the blackboard, let me have vertex number 1 and vertex number 2 and vertex number 3, something like this. This is Newton polygon, and this will be Newton broken line, so it will have two vertices. One corresponds to this edge of Newton polygon, another to this edge of Newton polygon. And well, this will be the x coordinates of the vertices will be the slopes. So this alpha 0, and this is alpha 1. Okay. Now, there is a certain Legendre transform, which I advertised last time, and then gamma of phi is well, almost the Legendre transform of n of phi. So, I mean, there is an involution which is just central symmetry, iota. Iota of the Legendre transform is a negative Legendre transform of n of negative alpha, central symmetry. And this involution gives you gamma of phi. So Legendre transform will be convex from below, just as n used to be. And iota of L will be convex from above. Okay. So what is the Legendre transform? Well, L can be applied to the graph of any convex function and gives the graph of some other convex function. So by definition, it is the following thing. So for any alpha, which is coordinate in the dual plane, we take the point t in the original plane. So here the coordinates t and s, and here it's alpha and I don't know what, say beta. So we'll take the point in the original plane depending on alpha, which maximizes the vertical distance from the graph of n to the line s equals alpha t. So it looks like this. We have this s, t, we have our function, and we have this line, s equals alpha t. And we need the maximal distance like this. Okay. So f of alpha t for fixed alpha equal to alpha t minus n of t must attain its maximum. And then we set gamma of alpha to be equal to f of alpha t, this maximal value. So let's consider an example. Just for quadratic functions. And maybe we will need a volunteer to consider this example. So are there any volunteers. It will be not a difficult example. It will be a quadratic function. Just as depicted there, parabola. And you will have some other examples in your home assignment. So say n of t equals to mt squared over 2. So the question is, what is gamma of alpha? So this parabola just goes through 0, through the origin. And here S equals mt squared over 2. So any volunteers? Pardon me?
Can you repeat the definition, please?
Of the Legendre transform? But I thought you must know it better than me. Maybe I made a mistake. So the definition is we want to find the value at alpha. Alpha is the slope of this line, and we take the maximal distance like this. So we consider this function, linear function minus our convex function, and we take its maximal possible value for all t. Alpha is fixed, t is arbitrary. Since the function is convex, it does attain its maximum value, and this, by definition, is the value of Legendre transform. So any volunteer to continue the lecture? Or we may stop right here to everybody's satisfaction. And to the utmost satisfaction. So in your home assignment, you will have some other power functions, but here it's just degree 2 quadratic function. So Serежа, maybe you will do it? But it's not something very fancy. You just you're second year student, right?
Yeah.
Junior, so to say. No, sophomore. And then you must still remember something from your high school years. So then you know how to find maximum. It's called an extremum. Yeah. So certain derivative must vanish. Yeah. So you're welcome. Maybe Kirill? I mean, maybe you? We must somehow profit from your presence, random as it is. And what grade are you in?
Same as.
Yeah, so you must have some reminiscences from high school yet.
What is going on? We're trying to find.
Trying to differentiate quadratic function.
Well, that's
А?
not hard.
Yeah, I also hope so.
Не, я не понимаю, а мы должны... Сейчас, еще раз, а что она из себя представляет? Мы просто ищем минимум
Alpha is a fixed parameter,
альфа, да? Ага.
and for this alpha, we find t, which gives maximum for this function. Namely, f of alpha t is alpha t minus m t squared over 2. And we must find t which gives the maximum value and this maximum value.
Ну, просто дифференцировать.
So, please.
Ну, я могу сказать, получится просто
Really?
альфа минус m.
Okay. So, df over dt is what?
Ну, альфа минус m.
Alpha minus m.
Минус...
Minus mt. Okay. So then this is equal to 0 if t is equal to what?
Alpha divided by m.
Very good. And then what is alpha? F of alpha and alpha divided by m? And can you subtract?
Yeah, that's
Yes.
alpha squared.
Yes.
No, alpha squared divided by 2.
Aha. Okay. So this is our function.
Вот так.
Yes.
Это все, да?
Yes. So the Legendre transform of mt squared over 2 is equal to alpha squared over 2m.
Ой, ладно, я понял.
Yeah.
Не, я понимал, что такое, ну, наша функция преобразования Лежандра.
Yes. This is the Legendre transform. In particular, Legendre's form of t squared over 2 is alpha squared over 2. And this is somewhat reminiscent of the fact that the Fourier transform of the function e to the whatever, I don't know, maybe negative x squared over 2 is the exponent of negative y squared over 2, maybe times some coefficient depending on the definition of Fourier transform. Because we need to normalize things. It could be I or pi or 2 pi I or 2 pi or pi over 2 or square root of pi, depends on our normalization conventions. Okay. Good. So, so the claim is once again that gamma of phi is this central symmetry applied to the Legendre transform of n of phi. But it contains absolutely the same information, but just it's packaged in some other way. So in particular, instead of slopes in the Newton polygon, we're talking just of the abscissas of vertices of the Newton-Broca line. Okay, it will be more convenient to us to think in terms of abscissas than in terms of slopes. Mm, okay. And now we will solve polynomial equations. Well, with coefficients. In CP, so to say, or in power series, like this. Well, this is already algebraically closed field. This is not yet. So I mean, to warm up, let's solve an equation x to the p minus x equals t. Well, again, I would need volunteers.
Как нам поможет тут?
Broken lines or polygons? No use, absolutely. No use at all. Just a warm-up exercise. Find a solution of this. I mean, this T is a formal power series. And we want to find the solution in the realm of formal power series. So, pardon me? 1 over p? No, y over p. Just in the formal power series. No, just integral degrees. Right? And then? Ah. Yeah, I mean, we're over characteristic p, so we just take pth powers and that's it, and they all cancel out. Maybe the only thing is the sign, the total sign, minus this, negative this. Yeah. Everything cancels out, right? Yeah, I mean, a plus b to the power p is a to the power p plus b to the power p. So here is the solution. Okay? Colli, you are this. You agree? Fine. Then then the next question is for t replaced by t inverse. So x to the p minus x is t inverse. How do you solve this? So, what's the...
Ну, минус. Ну, в общем, такой же x, только от t в минус p.
Ah, so it's negative t inverse plus t negative p plus t to the negative p squared plus so on. But that does not lie in the world of Laurent series. So it does not work. So what do we do? Next take. In fact, I think Kolya already mentioned this. So maybe you'll repeat your suggestion, Kolya. But I think you said it, no? Didn't you? No? I mean, you said in this framework, in this setup. So what is the leading term, so to say, of x? No, not 1. Why? We want t inverse. Okay, so maybe I should say that the solution will not be really a Laurent series. You will need to extract roots of t this time. Like if I asked x to the p equals t inverse, it would be just t to the power negative 1 over p. And this is the leading term. But now you have to correct. How do you correct? Yes. But still, it's not an exact solution. And so, yes. Because it has some support. So it's a formal series with support. And this is the set of powers with non-trivial coefficients. The support is equal to negative 1 over p, negative 1 over p squared, negative 1 over p cubed, and so on. And here the support was just 1, p, p squared, p cubed, and so on. And they have something in common. What do they have in common? The support is infinite, well, because it's a series, not a polynomial, but the supports have something in common. They're good in some similar respects. Yes, but these powers of p have some good behavior. Right, absolutely, yes. So this support S, well, it's a subset of rational numbers, is well ordered. Right? So any subset has minimal element, has the minimal element. Okay, so well, fp bar of t is the set of all series with well-ordered supports. So if they are discrete bounded from below, it's a sort of usual Laurent series, but they may have points of accumulation, like in this example, or even points of accumulation of points of accumulation, and so on. So maybe you've heard about ordinals in some basic logic course. So there are many ordinals, like omega is n, as far as I remember. But then there are like omega to the power of omega, or to the power of omega. Okay. And then the first theorem for today is that fp bar of t is algebraically closed. And the proof is well, take sorry, maybe before giving a proof of this, I should explain that this is a field. Is a field with respect to the usual sum. There is no problem with the sum, I guess, yeah, with the product. There is no problem with the product either. Yeah, but or maybe you should already at this stage use transfinite induction. And then you want to invert things. Well, to invert things, clearly it's enough to invert t itself. It will be just t inverse, or t to any power will be 2 to the negative power. But if you want to invert 1 plus something else, and this s is in strictly positive degrees, well, a alpha, t to the alpha, just use the geometric progression formula. Again, and maybe transfinite induction, if you wish. So indeed, it's a field. Moreover, it's a valued field. I mean, there is order from this field to Q. Maybe it's not P order, but T order. Yeah. So now take phi of x equal to the sum fi x to the I, some polynomial. So fi lies in our field. Maybe let me write f for fp bar to save precious moments of life. F of t. And I assume that f0 is not 0. I mean that it really starts with, it does have some constant term. Otherwise, I can divide by x, so it doesn't matter at all. And we will use the Newton broken line, gamma of phi. And if, say, psi is a root over phi in some normed extension over our field like this, then the T order of psi will be equal to the abscissa of a vertex of gamma. I mean, we proved this theorem before. We said that it was some slope or negative slope of the Newton polygon, but now after this Legendre transform, the slopes went to abscissas. So we know this, and let alpha naught be the maximal such abscissa. Okay, so L of alpha naught will be equal to L0 of alpha naught will be the order of F naught. I just erased this picture, so I had something like this, and this was 1/3. And this was alpha, beta. So this was beta equals 0. So this is my alpha naught. This is some other alpha. And well, beta is 0 just because my polynomial started with 1. But that does not necessarily start with 1. This constant term is not necessarily 1. It may have some order. Okay, so I don't assume that the ordinate of this point is necessarily 0. It's something. Namely, it's the T order of the constant term. Okay. Now let I be the set of degrees I, such that the lines assume the same value at alpha naught. So, I mean, in this case, just two lines intersect at this point, and the other one passed above. But in principle, there could be more than two lines intersecting at this point, something like this, yeah. And we need the set of all these lines. Okay, so we'll look for a solution x equals some series in T in the form x equals a alpha naught T to the alpha naught plus higher order terms. And then in your home assignment, you will have a particular example. So your base field will be complex numbers, and your coefficients will be just polynomials. So it will be essentially, effectively, a polynomial in two variables, in x and t. And you will need to solve for x in terms of t, but as a power series in t. And this will be a Puiseux series, so called. In cordistic 0, there are no such devastating effects as we just observed, and the supports are still discrete. You need to use some denominators. They're not necessarily integral, but they're still discrete. I mean, for a given Puiseux series, the denominators are all bounded. I mean, you can have some common denominator, like 1 over 100. And then it will be just some integral power divided by 100. This is classical Puiseux series for increasing 0. Okay. So the how to say it? Not the constant term, yeah. But well, the smallest order term of phi of x. I mean, we plug in this x into phi. Yeah, we want to get 0, but we will only get this by consecutive approximations. But we start with something. So at the first take, we get the smallest term equal to the sum over I in this set, capital I, f I, how should I say this? Maybe fi bar a alpha naught to the power I, where fi bar is the smallest order term of Fi. So Fi is equal to Fi bar T to the order of Fi plus higher order terms. Okay, so Fi bar is in my coefficient field F. Okay. So take A alpha 0 in F, a root of this equation. The sum over I in capital I, Fi bar, A alpha 0 to the power I is 0. So we want the a priori smallest term to vanish. Okay, for any alpha, for any A alpha naught, we'll get this, but we want this to vanish. And this is our first order approximation, so to say. Fine. This was it was the first approximation. And now we look for x in the form x equals this A alpha naught times p to the power, t to the power alpha naught plus A alpha 1 t to the power alpha 1 plus so on. Just repeating the above algorithm for the modified polynomial for f1 of x equal to phi of x plus A alpha naught t to the power alpha naught. Okay? And then in your home assignment, you will have to repeat this algorithm for 2 or 3 times. So you will find three first terms of the Newton algorithm for solving polynomial equation as a Puiseux series. Okay, so it remains to make sure that the smallest term of the root of the first generation, well, next generation polynomial will have t order bigger than alpha naught. And then we will be done by the transfinite induction. So we solved the very first approximation. Then we will consider the next term, and we only need to know that the order of this next term will be bigger, so that it's really the next approximation. Okay, so well, just lemma. The abscissa of the rightmost vertex over gamma of the next generation polynomial is strictly bigger than the previous abscissa alpha naught. That's what we have to check. And this is easy. So this way we will establish the Newton method of solving polynomial equations in terms of Puiseux series. And next time I will explain what modifications you need in case of Tate field in place of power series. I mean, power series with coefficients in finite field, well, it's quadratic P thing, and it's an analog of the maximal unramified extension. I mean, you just have to pass to Witt vectors from this, and then you will need to generalize this Witt vectors construction to the rational, well-ordered supports, and this will be sort of an explicit construction of Tate field. So next time, well, a model, an explicit model of Tate field. Instead of saying that it's some abstract operation of algebraic closure and topological completion, we just say that it's Witt vectors of F, but with rational, well-ordered supports. Okay, whatever it means. And now we just want to consider F. So now the proof of lemma. Well, we had f of x equals sum of fi x to the power I, and now we have f1 of x equal to the sum of fi1 x to the power I, where f I prime is fi plus y plus 1, choose 1, a alpha 0, t to the alpha 0, f I plus 1, plus I plus 2, choose 2, a alpha 0 squared, t 2 alpha 0, f I plus 2, and so on. Okay, which implies that f0 prime is equal to phi of a alpha 0 t to the alpha 0, and the t order of f0 prime is bigger than the t order of f0 just by construction. Okay, so our Newton broken line, in a sense, will lie higher. Yeah, because the rightmost part of the Newton broken line is always at the height equal to the t order of f0. So this is beta of alpha naught. Well, maybe not gamma of alpha naught. Yeah, and this should be not beta, this should be gamma, in fact. Okay, so in a sense, it grows higher. Okay, now let k be the maximum of I, such that Li of alpha 0 is L of alpha 0. Just we consider this set capital I, and we just take the maximal k in this set. Then L prime for the well, attached to the polynomial phi prime, L prime k over alpha 0 will be equal to the t order of f prime k plus k times alpha 0. And this will be the t order of f k plus k alpha 0. And this will be just L k of alpha 0, since all the terms of this equality except the first one. Well, maybe I don't know how to say it. Have the higher order. Okay, and that's it. So we know once again that L prime k of alpha naught is equal to Lk of alpha naught, and we also know that the order of f prime 0 is bigger than the order of f0. So these two facts automatically imply just what we wanted, that the alpha naught prime is bigger than alpha naught, because it grew higher, and so it lies on this line, so it must be to the right. This must be, this alpha naught prime must be bigger than alpha naught. That's it. So we proved the classical result, though it's not maybe too classical. I think it goes back to 80s. And I don't remember even whom it goes back to. Some Romanian mathematician. No. And next time we'll discuss this with vector analog, which comes just for free. Although it will use some arithmetic, but in this arithmetic you only need to know that all the binomial coefficients are integers, nothing else. So they will not spoil the p order. And everything else will be automatic. You only need to explain somehow how to perform operations with with vectors with rational support. Okay. Thank you for today.